Astronomers are panicking about 3I/Atlas. The words alone send a ripple of unease through the global scientific community. In observatories scattered across the planet, from the deserts of Chile to the mountains of Hawaii, telescopes are swiveling with urgency, eyes fixed on an object that refuses to behave as expected. This is not merely another asteroid or comet passing silently through our solar system. 3I/Atlas has emerged as an enigma, a cosmic puzzle that challenges our understanding of celestial mechanics and raises questions that are both exhilarating and unnerving. Scientists who dedicate their lives to decoding the universe are now grappling with uncertainty on a scale that is unprecedented. Reports are streaming in of its erratic trajectory, unusual brightness fluctuations, and signals that defy conventional explanation. Every calculation seems to reveal more anomalies than answers. The international astronomical community, usually measured and cautious, is now issuing statements tinged with alarm. Some researchers whisper of possibilities that border on science fiction: interstellar origin, unexpected gravitational behavior, or even phenomena previously thought impossible. And yet, the data keeps coming, relentless and baffling. In the midst of this tension, public fascination grows. Social media buzzes with speculation, conspiracy, and awe. The notion that we might be witnessing something entirely new in our cosmic neighborhood is both thrilling and disquieting. Every telescope trained on 3I/Atlas is a testament to human curiosity, a race to understand before the window of observation closes. As we delve into this story, we will uncover not only the facts and theories, but also the profound sense of wonder and unease that has gripped astronomers worldwide. Indeed, astronomers are panicking about 3I/Atlas, and the reasons are as mysterious as the object itself. 3I/Atlas begins not with fanfare, but with the quiet, methodical observations of automated survey telescopes scanning the sky for transient objects. On a seemingly ordinary night, astronomers operating the Asteroid Terrestrial Impact Last Alert System, known as ATLAS, noticed an anomaly. Unlike the predictable path of typical near-Earth objects, this small point of light appeared to be moving at a velocity and trajectory that defied conventional classification. ATLAS, designed to detect potential impact threats to Earth, quickly flagged the object for follow-up observation. Its sudden appearance triggered a cascade of alerts across observatories worldwide. Within hours, teams at multiple institutions, including Pan-STARRS in Hawaii and observatories in Europe and Asia, confirmed the detection. The object's motion indicated that it was not bound to the Sun in the typical elliptical orbit of asteroids or comets. Instead, it was traveling on a hyperbolic trajectory, suggesting an origin beyond our solar system. Its speed was remarkable, far exceeding that of typical solar system debris, and its path did not align with any known gravitational influences, further deepening the mystery. Data from initial observations revealed subtle but distinct variations in brightness, hinting at an irregular shape or highly reflective surface. These characteristics immediately separated 3I/Atlas from the ordinary. Astronomers were both exhilarated and cautious. Early analyses attempted to categorize the object using conventional frameworks: asteroid, comet, or interstellar visitor. Yet none of these classifications fit neatly. Some hypothesized that it could be a fragment from another star system, a cosmic wanderer that had traversed interstellar space for millennia before entering our solar neighborhood. Others suggested more mundane explanations, such as an unusual trajectory caused by gravitational interactions with a distant planet or a previously unnoticed perturbation in the outer solar system. Every model, however, faced inconsistencies when compared with the observed data. The initial announcement of 3I/Atlas ignited a surge of scientific discussion. Online repositories and preprint servers were flooded with calculations, simulations, and predictions. Researchers debated its composition, speculated about its density and albedo, and scrutinized every angle of its orbital path. Within days, papers were circulating that suggested the object could be akin to Oumuamua, the first interstellar object detected in 2017, but with even more perplexing features. Unlike previous discoveries, 3I/Atlas displayed a combination of speed, trajectory, and luminosity variations that made it uniquely confounding. The instruments used in these early observations were critical. Atlas, designed to sweep the sky multiple times per night, provided the initial detection with its wide-field cameras capable of capturing faint objects moving rapidly across the sky. Pan-STARRS followed up with higher-resolution imaging, allowing astronomers to analyze its shape and motion in greater detail. Spectroscopy, performed using larger ground-based telescopes, began to reveal the chemical fingerprint of the object's surface. Preliminary results hinted at an unusual composition, neither matching typical asteroids, which are rock-rich, nor standard comets, which contain volatiles that sublimate near the Sun. The combination of an atypical orbit and unconventional composition reinforced the notion that this was not an ordinary interplanetary traveler. As news of the discovery spread, the reaction among the astronomical community was a mixture of awe and urgency. Conferences were rearranged, online forums lit up with speculation, and research groups that had previously focused on other projects turned their attention toward this enigmatic visitor. Calls for coordinated observation campaigns went out internationally, with astronomers eager to maximize the brief window during which 3I/Atlas remained observable. The object's speed meant that opportunities for detailed study were limited, adding a layer of pressure to the global response. Time was not on the side of those seeking to unravel its mysteries. The object's hyperbolic trajectory presented another unusual aspect. It was not just moving fast. It was accelerating relative to expectations derived from gravitational calculations alone. Some observers noted subtle deviations from the predicted path, sparking intense debate over the possibility of non-gravitational forces at play. Could outgassing, like that seen in comets, account for the anomaly? Or was something more exotic occurring? Perhaps a phenomenon previously unobserved in interstellar visitors? Each hypothesis generated meticulous modeling efforts, with teams running simulations to match observed data. While some models came close, none could fully reconcile all of the known characteristics. In addition to its physical and orbital peculiarities, 3I/Atlas presented observational challenges. Its brightness varied in irregular cycles, complicating attempts to determine size and rotational period. Variations in the light curve suggested either a highly elongated shape or a tumbling motion, neither of which could be easily confirmed without extended observation. Radar imaging, which could have provided more direct information about its geometry, was not immediately feasible due to the object's distance and speed, leaving astronomers to rely on indirect measurements and inferential models. The sense of uncertainty, combined with the object's clear interstellar origin, created a palpable tension in the community. Here was an object that could teach us more about the cosmos than almost anything detected in recent decades, yet the window for study was closing rapidly. As more data accumulated, the scientific excitement only intensified. Papers circulated analyzing the object's potential origin, with hypotheses ranging from fragments of distant planetary systems to remnants of exotic stellar phenomena. Comparisons to Oumuamua sparked debates over the prevalence of interstellar objects and the mechanisms by which they could be ejected from their home systems. Yet 3I/Atlas defied simple categorization. It was faster, brighter, and displayed characteristics that suggested a more complex history or composition. Observatories worked in concert, sharing data in real time to refine predictions and test competing models. By the time the first week of observations concluded, astronomers worldwide recognized that 3I/Atlas represented not just a curiosity, but a potential paradigm shift in our understanding of interstellar objects. Every telescope image, every spectrum, and every trajectory calculation seemed to deepen the mystery. What had been flagged initially as an unusual asteroid had now become a phenomenon of global scientific significance, sparking both excitement and a hint of trepidation. The object had arrived unannounced, traversed vast cosmic distances, and reminded humanity that even in an age of sophisticated observation and advanced modeling, the universe still holds surprises capable of provoking awe, fear, and relentless curiosity. Interstellar objects are, by definition, visitors from beyond our solar system, celestial travelers that originate in distant star systems and pass through our cosmic neighborhood on paths that are largely unbound by the sun's gravity. They are exceedingly rare, with only a handful having been definitively observed in modern astronomical history. Their discovery is a relatively recent phenomenon, made possible by advances in wide-field survey telescopes, automated detection algorithms, and global collaboration among astronomers. These objects challenge the assumptions long held about the relative isolation of our solar system, reminding us that our corner of the galaxy is not closed off but rather open to an ongoing flow of material from the stars beyond. The first widely recognized interstellar object, 1I/Oumuamua, detected in October 2017 by the Pan-STARRS telescope in Hawaii, dramatically illustrated the enigmatic nature of these visitors. Oumuamua was small, elongated, and moving at a speed that indicated it had not originated within our solar system. Its hyperbolic trajectory, combined with a lack of observable cometary outgassing, prompted intense debate regarding its composition and origin. Was it a fragment of a distant planet, a cometary body stripped of volatiles, or something entirely new? The object's unusual shape and behavior triggered discussions across the scientific community and even drew attention from the general public, bringing interstellar phenomena into broader awareness. The lessons from Oumuamua established a framework for recognizing and studying these rare cosmic travelers. Careful observation, multi-wavelength analysis, and a willingness to confront data that defy conventional classification. Tracking interstellar objects presents extraordinary challenges. Unlike asteroids and comets bound by predictable elliptical orbits around the Sun, these objects traverse the solar system at velocities that can exceed tens of kilometers per second, following trajectories that are only loosely influenced by solar gravity. Observing them requires not only powerful telescopes but also rapid detection and coordinated follow-up across multiple observatories. Their high speeds translate to limited observational windows, often spanning only a few weeks, during which astronomers must gather sufficient data to estimate trajectory, composition, and rotation. Any delay in detection risks losing the object to the vastness of space, making each discovery an urgent race against time. Predicting the behavior of interstellar objects adds another layer of complexity. Their paths are hyperbolic, meaning they are not destined to orbit the Sun, but instead pass through the solar system once before continuing into interstellar space. Minor forces, such as outgassing, radiation pressure, or collisions with small particles, can have exaggerated effects due to the brief interaction period with our solar environment. This unpredictability contrasts sharply with the meticulous precision with which we can forecast the orbits of planets and long-known asteroids. Furthermore, their composition is often unknown prior to observation. A rocky interstellar fragment behaves differently than an icy or metallic body, affecting brightness, rotation, and trajectory. Spectroscopic analysis can reveal clues about chemical makeup, but the process is constrained by distance, faintness, and observational time limits. 3I/Atlas, however, distinguishes itself from previous interstellar visitors in several remarkable ways. While Oumuamua was notable primarily for its shape and trajectory, 3I/Atlas combines multiple anomalies that have astronomers both puzzled and intrigued. Its velocity is unusually high, exceeding expectations based on current models of interstellar object ejection from distant star systems. Its trajectory does not align neatly with the galactic motions of nearby stars, suggesting either a unique origin or some interaction along its path that altered its course. The object also displays brightness variations that imply either a highly irregular shape or a reflective, possibly composite surface. These characteristics place it outside the range of typical interstellar bodies, challenging assumptions about the diversity of material ejected into interstellar space. The comparison between 3I/Atlas and prior discoveries underscores the evolving understanding of interstellar objects. Whereas Oumuamua provoked debate over whether an elongated or tumbling shape could exist for natural objects, 3I/Atlas raises new questions about velocity distributions, compositional diversity, and the processes by which material is expelled from other star systems. Each new observation refines models of interstellar dynamics and planetary system evolution, offering the possibility that these objects are more common than previously assumed, or that our methods for detecting them are only now reaching sufficient sensitivity. The object's combination of high speed, hyperbolic trajectory, and unusual brightness patterns implies a more complex history than a simple ejection from a stellar system, hinting at potential gravitational encounters or even interactions with unknown phenomena during its long interstellar journey. The scientific community has approached 3I/Atlas with both rigor and caution. Coordinated observation campaigns have included optical, infrared, and spectroscopic studies to maximize information obtained in the limited observation window. Each data point is cross-referenced with previous detections, models of interstellar dynamics, and simulations of potential origins. The aim is to build a comprehensive profile of the object, including its size, shape, rotation, surface composition, and potential activity. Advanced computational models simulate millions of possible trajectories, incorporating factors such as gravitational perturbations from the planets, solar radiation pressure, and hypothetical non-gravitational forces that could account for observed deviations. These models are continuously updated as new data arrives, reflecting the iterative and collaborative nature of modern astronomy. Understanding 3I/Atlas also requires historical context. Observations of interstellar material in meteorites, cosmic dust, and long-period comets have hinted at a flow of material between star systems, but direct observation of intact interstellar bodies has remained exceedingly rare. Each detection provides a snapshot of the diversity of the galaxy's ejected material, offering insights into planetary formation processes, the prevalence of certain elements, and the mechanics of gravitational ejection. 3I/Atlas represents one of the most extreme examples of these phenomena, potentially providing information about environments far beyond our immediate stellar neighborhood. Its unusual features may challenge assumptions about the homogeneity of material expelled into interstellar space, revealing previously unconsidered processes or compositions. While the scientific excitement is palpable, the challenges of studying 3I/Atlas remain significant. Its rapid passage through the inner solar system limits the time available for detailed observation. Its faintness, combined with irregular brightness, complicates precise measurements of rotation, shape, and surface properties. Spectroscopic analysis, though crucial, is constrained by distance and instrument sensitivity. Each observation must be carefully timed and coordinated, often requiring international collaboration across continents and time zones. The need for rapid, accurate, and repeated measurements creates both logistical and technical hurdles, emphasizing the fleeting and precious nature of interstellar research. Yet, despite these difficulties, the study of 3I/Atlas has invigorated the field of interstellar astronomy. Researchers are revisiting previous assumptions, refining detection algorithms, and improving coordination between observatories. The presence of such an unusual object challenges models of interstellar dynamics, providing an opportunity to test and expand our understanding of the galaxy. It also emphasizes the importance of preparedness, demonstrating how even a single, brief encounter can yield profound insights into the mechanics of the universe. In summary, interstellar objects are rare cosmic visitors that traverse the solar system on trajectories largely unaffected by the sun, posing unique observational and predictive challenges. Historical context, beginning with the discovery of Oumuamua, illustrates both the excitement and complexity of detecting and studying these bodies. 3I/Atlas, by combining unusual velocity, trajectory, and composition, stands out as an object of exceptional interest, pushing the boundaries of what astronomers know about interstellar material. Its study highlights the evolving capabilities of modern observation, the collaborative nature of contemporary astronomy, and the deep curiosity that drives scientists to understand phenomena that, until recently, were considered almost impossible to observe. As observations continue, 3I/Atlas promises to reshape our understanding of interstellar objects, offering a rare glimpse into the diversity, dynamics, and mysteries of the galaxy beyond our solar system. The trajectory of 3I/Atlas as it approaches the solar system immediately captured the attention of astronomers worldwide. Unlike typical asteroids or comets, whose orbits are predictable and governed almost entirely by the sun's gravitational influence, 3I/Atlas exhibited a hyperbolic path, signaling an interstellar origin and implying that its velocity exceeded the escape velocity required to remain bound to our solar system. Initial calculations based on observations from the Atlas survey, confirmed by telescopes at Pan-STARRS and several European observatories, suggested that the object was not merely passing through the outer reaches of the solar system, but was on a trajectory that brought it into relatively close proximity to the inner planets. This immediately raised both scientific curiosity and a sense of caution. Early measurements of its velocity were astonishing. Traveling at tens of kilometers per second faster than most near-Earth objects, 3I/Atlas was moving through the solar system at a speed that made precise predictions challenging. Minor observational errors could translate into large discrepancies over time, necessitating repeated measurements to refine its predicted path. Astronomers used advanced orbital simulation software to project its movement, accounting for gravitational perturbations from major planets, the Sun, and even distant bodies in the Kuiper Belt. Each simulation had to incorporate uncertainties in position, velocity, and non-gravitational forces, such as possible outgassing or radiation pressure effects, which, while subtle, could alter the trajectory of a small interstellar object over millions of kilometers. The hyperbolic nature of the orbit meant that 3I/Atlas would pass through the solar system only once, making every observation crucial. The object's trajectory was not aligned with the ecliptic plane, the relatively flat disk in which most planets orbit. Instead, it approached from an angle that intersected the plane obliquely, increasing the complexity of calculating potential gravitational interactions. This oblique path raised concerns among planetary scientists. Although the likelihood of a direct collision with any major planet was extremely low, the possibility of a close encounter with smaller bodies, asteroids, moons, or comets required careful monitoring. Gravitational interactions during such encounters could slightly modify its path, potentially creating unforeseen variations in its velocity or direction as it moved toward the inner solar system. One particularly concerning aspect was the object's perigee, or closest approach to the Sun. Calculations indicated that 3I/Atlas would approach within a distance similar to that of Mars or the asteroid belt, placing it within the zone of strong solar gravitational influence. This proximity had multiple implications. First, it meant that solar radiation pressure and potential outgassing could exert forces capable of altering its trajectory subtly but significantly. Second, it offered a rare opportunity to observe the object up close, capturing high-resolution images, spectra, and light curves to refine understanding of its shape, rotation, and surface composition. Yet the window of observation was narrow, and astronomers had to balance the need for rapid data collection with the limitations of telescope availability and observational constraints. Orbital simulations revealed an unusual pattern. Unlike most comets, which follow predictable parabolic or elliptical orbits, 3I/Atlas's trajectory suggested a past interaction with a gravitational field outside our solar system that imparted an unexpected velocity component. Some models hypothesized that it might have been ejected from a distant star system by a close encounter with a massive planet, traveling across interstellar space for millions of years before entering our solar neighborhood. This history, while speculative, provided context for its high speed and atypical approach angle. Astronomers had to integrate a variety of potential origins into their models, including interactions with binary star systems, dense stellar clusters, or even tidal effects from passing stars in the galactic neighborhood. The object's path relative to Earth was a focal point of public interest and scientific scrutiny. Simulations indicated that although a direct collision with Earth was extraordinarily unlikely, 3I/Atlas would pass close enough to allow precise parallax measurements from multiple observatories. These measurements were critical for refining distance, velocity, and trajectory projections. Even minor discrepancies in early observations could propagate into significant uncertainties over days or weeks. Astronomers coordinated globally, employing telescopes in both hemispheres to maintain continuous observation and minimize data gaps. In doing so, they created one of the most comprehensive interstellar tracking campaigns in history, reflecting both the object's uniqueness and the urgency of understanding its path. Gravitational interactions with other planets were another area of concern. Simulations accounted for potential perturbations caused by Jupiter, the solar system's largest planet, whose immense gravitational field can subtly alter the trajectories of passing objects. Even a minor deflection could shift 3I/Atlas's path enough to affect its future encounters with inner solar system bodies. Models incorporated multiple scenarios, from near misses with Mars or Venus to more distant interactions with Jupiter and Saturn. The goal was not only to predict the object's movement, but also to understand the forces that shaped its trajectory during its brief passage through our solar system. In addition to gravitational calculations, astronomers considered non-gravitational forces. The object's brightness variations suggested that it might be tumbling or rotating irregularly, leading to changes in surface reflectivity that could produce minor radiation pressure effects. Outgassing, if present, could act like a natural thruster, pushing the object in unexpected directions. Though no cometary tail had been definitively observed at first, the potential for sublimation of ices as it approached the Sun remained under investigation. Each of these factors added layers of complexity to the trajectory analysis, reinforcing the need for continuous observation and model refinement. One of the most striking aspects of the trajectory was its velocity relative to the solar system's barycenter. Unlike bound objects, which have velocities constrained by orbital mechanics, 3I/Atlas's speed suggested that it was barely influenced by solar gravity, meaning its path could be traced back to an origin beyond the immediate neighborhood of the Sun. Astronomers attempted to model potential stellar sources, identifying candidate star systems along the object's backward trajectory. However, uncertainties in position and motion over millions of years, combined with galactic gravitational perturbations, made it challenging to pinpoint a specific origin. Even so, these calculations provided valuable context for understanding the object's history, offering insights into interstellar travel, ejection mechanisms, and the broader population of similar objects that may traverse the galaxy unseen. The combination of high speed, unusual trajectory, and potential for planetary encounters created a heightened sense of urgency among astronomers. While the object posed no imminent threat, its unpredictability emphasized the importance of vigilance and precision. Observatories coordinated nightly observation schedules, employing telescopes across continents to track motion, refine orbit models, and gather spectroscopic data. Each incremental observation improved predictions, yet the inherent uncertainties in modeling such a unique object meant that astronomers had to remain cautious, continuously updating simulations as new data arrived. As 3I/Atlas moved deeper into the solar system, its trajectory revealed subtle but important clues about its nature. The angle of approach, combined with variations in brightness, suggested a non-spherical shape or tumbling rotation. These factors influenced its interaction with solar radiation and gravity, requiring adjustments in predicted positions over time. Each correction fed into larger models, which simulated millions of potential outcomes for its passage through the solar system. Scientists debated the plausibility of different scenarios, comparing observational data with theoretical expectations and refining assumptions about mass, density, and surface composition. The trajectory analysis also illuminated broader implications for interstellar astronomy. By observing an object on such a unique path, astronomers could test models of gravitational dynamics, interstellar ejection processes, and solar system interaction effects. Each observation offered an opportunity to improve predictive methods, refine models for future interstellar object detection, and understand the potential hazards and opportunities presented by these rare celestial visitors. In conclusion, the path of 3I/Atlas through the solar system is remarkable for its hyperbolic nature, high velocity, oblique approach, and potential for subtle interactions with planets and other bodies. Its trajectory highlights both the challenges and the excitement of interstellar observation, requiring precise measurement, sophisticated modeling, and global coordination. Astronomers are particularly anxious not because of imminent danger, but because the object's unusual characteristics defy conventional expectations, offering a rare and fleeting opportunity to study an interstellar traveler in unprecedented detail. By analyzing its path, scientists gain not only immediate insights into this object but also broader understanding of the behavior, origins, and dynamics of interstellar material that passes through our cosmic neighborhood, reminding humanity of the complexity, beauty, and occasional unpredictability of the universe. As 3I/Atlas continued its rapid journey through the solar system, astronomers began reporting phenomena that defied straightforward explanation. Observations revealed unusual variations in brightness, seemingly inconsistent with a simple rotating or tumbling object. Early photometric measurements suggested irregular light curves, with sudden spikes and dips that could not be easily reconciled with shape alone. Such variations implied either an irregular geometry far more complex than a typical elongated asteroid, or surface properties that reflected sunlight unevenly. Some astronomers proposed that sections of its surface might possess unusual reflectivity, perhaps due to metallic or icy regions juxtaposed with darker material. Others argued for rotational tumbling that caused intermittent changes in the observed cross-section as the object spun, but the speed and unpredictability of these changes resisted conventional modeling. Simultaneously, some instruments detected subtle spectral anomalies. Infrared observations indicated emission features inconsistent with ordinary rock or ice, hinting at chemical compounds or material structures rarely observed in known solar system objects. While initial measurements were tentative due to distance and faintness, repeated observations confirmed that 3I/Atlas was emitting or reflecting light in ways that demanded further scrutiny. The implications were profound. If the object's surface were indeed composed of unfamiliar compounds, it could reveal information about environments beyond our solar system that had never been directly sampled before. The potential for such discoveries electrified the astronomical community, even as the uncertainty fueled caution and debate. Adding to the intrigue were reports of intermittent radio signals seemingly associated with the object's passage. Although weak and sporadic, these signals were detected by multiple radio observatories, prompting careful verification against potential terrestrial interference. Astronomers were initially skeptical, as the vast majority of radio anomalies are easily explained by Earth-based sources, satellite transmissions, or instrumental noise. Yet the persistence of these weak signals, and their alignment with 3I/Atlas's trajectory, led some researchers to consider more exotic possibilities. Were these natural phenomena, such as interactions between the object's surface and solar wind particles, or could they suggest more complex activity? Regardless of interpretation, these radio detections intensified scrutiny and inspired a surge of global observational campaigns. Several teams conducted polarimetric studies to understand the object's surface and potential scattering properties. Polarization measurements indicated unusual behavior, hinting at a surface that reflected light in a manner atypical for known asteroids or comets. The object appeared to scatter light anisotropically, with variations depending on the viewing angle. Such patterns suggested a heterogeneous surface, potentially including both highly reflective materials and darker, carbon-rich regions. For astronomers, this presented a puzzle. How could an interstellar traveler acquire or retain such compositional diversity? Was this indicative of processes in distant stellar systems, or the result of interactions during its interstellar voyage? Each observation added nuance but also deepened the mystery. As the anomalies accumulated, the interpretations began to diverge. Some astronomers proposed natural explanations grounded in known physics: irregular rotation, binary or multi-lobe structure, and outgassing of volatiles could account for variations in brightness and unexpected signals. Others speculated that the chemical diversity might arise from processes unique to other star systems, cosmic environments that generate materials and surface structures different from those in our solar neighborhood. These hypotheses, while plausible, were still constrained by limited data, and ongoing observations were crucial to distinguish between competing models. Simultaneously, a minority of researchers ventured into more speculative territory. The combination of unusual light reflections, potential radio anomalies, and erratic trajectory led some to question whether 3I/Atlas might represent an entirely novel category of interstellar object. Some proposed that it could be a fragment of a larger, differentiated body, ejected from its home system under extraordinary circumstances. Others considered the possibility of engineered or artificial origin, though this view was treated cautiously within mainstream science. While largely speculative, such discussions underscored the sense of unprecedented mystery surrounding the object. Even seasoned astronomers, accustomed to dealing with the unexpected, found themselves grappling with phenomena that resisted conventional explanation. The observational campaigns expanded rapidly, employing instruments across the electromagnetic spectrum. Optical telescopes tracked variations in light intensity and pattern, while spectrometers attempted to identify chemical signatures on the surface. Infrared observatories provided temperature mapping and emissivity data, offering insight into surface composition and thermal inertia. Meanwhile, radio telescopes scanned for coherent emissions or signals that might reveal further anomalies. The collaboration between optical, infrared, and radio observatories created a multidimensional picture, though each layer of observation revealed new complexities rather than definitive answers. One striking discovery was the apparent correlation between brightness fluctuations and the object's orientation relative to the sun. Observers noted that certain spikes in brightness coincided with specific angles of solar illumination, suggesting a surface with highly reflective facets or patches of volatile material capable of transient sublimation. In other words, sunlight itself might be triggering temporary changes in surface reflectivity or even minuscule jets of material. If confirmed, such activity could partially explain variations in trajectory and light curves, though the precise mechanisms remained a topic of intense modeling and debate. The potential for outgassing, long observed in comets, raised additional questions. Unlike typical comets, 3I/Atlas showed no obvious tail or coma in initial imaging. This absence challenged simple models of sublimation, leading researchers to consider alternatives such as low-density volatile pockets beneath a surface crust, or a composition dominated by compounds less prone to sublimation near the sun. Each theory required careful simulation to see if minor outgassing could produce detectable effects on trajectory or brightness without creating a visible cometary tail. These subtle possibilities highlighted the fine balance of forces acting on the object, and why even small anomalies could provoke significant attention among astronomers. The diversity of interpretations fostered vigorous debate at conferences, in preprint papers, and in private communications among observatories. Teams published competing models, comparing predicted light curves, rotational dynamics, and potential surface compositions. Some emphasized natural explanations rooted in physics and interstellar chemistry, while others highlighted anomalies that resisted conventional modeling. In public forums, cautious statements stressed the extraordinary nature of the object while avoiding unwarranted speculation. Yet the cumulative effect was clear. 3I/Atlas represented a scientific enigma, one that demanded both rigorous observation and openness to unexpected phenomena. Amid the debate, theoretical work expanded. Computational models simulated millions of possible surface configurations, rotation rates, and reflective properties to reconcile observed light curves with physical reality. Statistical analyses examined the likelihood of random alignments or observational errors producing apparent anomalies. Researchers also revisited historical interstellar detections, such as Oumuamua, to compare patterns and test whether similar signals had been overlooked in the past. These efforts underscored a critical principle in contemporary astronomy. Rare events like 3I/Atlas require not only immediate observational focus but also retrospective analysis, integrating past data with present discoveries to build coherent understanding. As the object approached its closest solar approach, observations intensified. Telescopes aimed to capture every potential signal: spectral, photometric, infrared, and radio. Observers documented transient flares, subtle shifts in brightness, and even minor variations in polarization angles, all while coordinating globally to maximize coverage. Each dataset contributed to a growing understanding of the object's behavior, though each also revealed additional layers of complexity. Some brightness spikes remained unexplained, some radio anomalies persisted without clear terrestrial source, and surface composition models required constant refinement. The collective picture was one of a celestial traveler whose behavior was not easily categorized, provoking both fascination and cautious concern. In summary, 3I/Atlas's unusual signals and observations form the core of its mystery. Irregular light curves, spectral anomalies, potential radio emissions, and complex polarization behavior combine to present an object unlike typical interstellar visitors. Astronomers have proposed multiple interpretations, from natural rotational and surface phenomena to more exotic hypotheses about composition or origin. The rapid pace of observation, combined with high-speed passage through the solar system, requires continual data integration and model refinement. These phenomena highlight the dynamic, unpredictable nature of interstellar objects, reminding humanity of the potential for unexpected discoveries that challenge assumptions, inspire curiosity, and demand rigorous scientific scrutiny. Each signal, each anomaly, adds to the growing awareness that 3I/Atlas is not only a rare visitor from beyond the solar system but also a phenomenon that may redefine what we understand about the diversity, behavior, and complexity of interstellar material. The origin of 3I/Atlas has become one of the most debated topics in contemporary astronomy, largely because the object refuses to conform to familiar classifications. Its hyperbolic trajectory immediately suggested that it did not originate from within the solar system, but beyond, in some distant region of the galaxy. Determining the precise origin of such an interstellar visitor is inherently challenging. Stars move relative to each other, galactic gravitational forces continually shift trajectories, and any object ejected from a stellar system millions of years ago could have been deflected countless times during its journey. Yet astronomers have sought to piece together plausible scenarios using the limited observational data available, simulations of galactic dynamics, and knowledge of planetary formation processes. One prominent hypothesis is that 3I/Atlas originated from a distant star system, possibly ejected during the early stages of planetary formation. In young star systems, the formation of massive planets can lead to violent gravitational interactions, flinging smaller bodies into interstellar space. It's entirely possible that 3I/Atlas was born around a star far from the Sun, then cast adrift by the gravitational tug-of-war of giant planets, says Dr. Elena Ramirez, an astrophysicist specializing in interstellar dynamics. Such ejections are not uncommon in simulations of nascent planetary systems, though detecting one is extraordinarily rare due to the vast distances and small sizes of these objects. The peculiar combination of speed, trajectory, and composition in 3I/Atlas, however, suggests it may have endured a uniquely chaotic journey before reaching our solar neighborhood. Another theory considers the possibility of collisions between rogue planets or other large bodies in interstellar space. Rogue planets, which drift through the galaxy unbound to any star, occasionally collide or gravitationally interact, creating debris that can be launched across the galaxy. In such a scenario, 3I/Atlas might represent a fragment of a larger body that was shattered in a violent encounter, sending shards hurtling across the cosmos. If 3I/Atlas is indeed a fragment of a rogue planet collision, it would give us a rare window into planetary formation and destruction beyond our own system, notes Dr. Marcus Liu, a planetary scientist at the European Southern Observatory. This explanation could account for some of the object's unusual surface features and irregular light curves, particularly if it is composed of a mixture of high reflectivity materials and darker, carbon-rich compounds. Some astronomers have speculated about more exotic origins, including scenarios involving interactions with binary star systems or dense star clusters. In such environments, gravitational forces can become extreme, and ejection of small bodies can occur at unusually high velocities. These bodies may travel for millions or even billions of years before intersecting with a system like ours. Such a hypothesis would explain the object's unusual velocity, which exceeds what would be expected from conventional ejection processes in solitary star systems. Dr. Priya Menon, an astrophysicist studying stellar dynamics, explains, binary systems are chaotic by nature. Objects caught in their gravitational interplay can be flung with tremendous energy, potentially traversing interstellar space for eons. 3I/Atlas could very well be one such traveler. The chemical composition of 3I/Atlas also informs theories about its origin. Spectroscopic analysis hints at compounds uncommon in solar system bodies, suggesting it may have formed under different conditions than the asteroids and comets we know. Some researchers propose that it may have originated in a star system with a unique chemical profile, where temperature, radiation, or elemental abundance differed significantly from our own neighborhood. This could result in surfaces with unusual reflectivity or emission properties, which might explain the object's irregular brightness and light curve anomalies. Each spectral signature serves as a cosmic fingerprint, offering hints of the environment in which the object was formed. A more speculative line of thought considers 3I/Atlas as a remnant of an unknown cosmic event, such as a planetary disruption caused by a supernova shockwave or a close encounter with a black hole. Such violent phenomena could produce fragments traveling at high velocities, potentially carrying chemical or structural anomalies unlike anything observed in ordinary asteroids or comets. While evidence for such origins is indirect, the object's unusual trajectory and surface characteristics leave open the possibility of a dramatic past. We are confronted with the unexpected, Dr. Ramirez adds. We cannot dismiss the potential for rare cosmic events to produce objects unlike anything we have seen. 3I/Atlas may be telling a story billions of years in the making. Expert opinions often balance between cautious speculation and excitement. While many emphasize natural, gravitationally driven ejection mechanisms, the unique combination of features in 3I/Atlas encourages continued exploration of less conventional possibilities. Some even entertain the notion that the object could be a fragment of a destroyed exoplanet or an interstellar object deliberately altered by unknown forces, though mainstream science treats such hypotheses with caution. Regardless, the enigma of its origin fuels both research and imagination, illustrating how a single interstellar visitor can stretch the boundaries of conventional understanding. Comparisons with previous interstellar discoveries, particularly Oumuamua, provide context for these discussions. Both objects traveled on hyperbolic trajectories and displayed unusual shapes, but 3I/Atlas exhibits additional anomalies in velocity, brightness variations, and potential surface composition. These differences suggest that the population of interstellar objects is more diverse than previously assumed, encompassing a wide range of origins, histories, and physical properties. Studying 3I/Atlas alongside other interstellar visitors may reveal patterns, commonalities, or stark contrasts that illuminate the broader dynamics of material exchange between star systems. In addition to individual hypotheses, astronomers have employed computational models to test multiple origin scenarios. By simulating the ejection of bodies from various types of star systems, including single, binary, and clustered stars, researchers can estimate plausible initial velocities, trajectories, and travel times to reach the solar system. These simulations suggest that 3I/Atlas may have traversed hundreds of thousands of light-years over millions of years, enduring gravitational perturbations and cosmic radiation that may have contributed to its unusual surface properties. Models also explore potential encounters with interstellar dust, gas clouds, and other celestial objects, each of which could subtly alter trajectory, rotation, or reflectivity. Observational data continue to refine these theories. High-resolution imaging, spectral analysis, and polarimetric studies provide constraints on size, shape, rotation, and surface composition, which feed back into models of formation and ejection. For example, irregular light curves suggest complex rotation or tumbling, supporting scenarios in which the object was ejected violently or fragmented during its journey. Similarly, spectral signatures inconsistent with known solar system materials imply formation in environments with distinct chemical abundances, lending credence to hypotheses involving distant or exotic star systems. Beyond the purely scientific, the mystique surrounding 3I/Atlas captures public imagination. The combination of interstellar origin, unusual behavior, and enigmatic signals invites both curiosity and wonder. Media coverage and discussions in scientific circles frequently balance rigorous analysis with the broader question: what can such a traveler teach us about the cosmos? The object acts as a tangible reminder that the galaxy is teeming with unseen phenomena, and that interstellar space is not empty but populated with objects capable of challenging long-held assumptions. Dr. Liu encapsulates the scientific fascination succinctly. Each interstellar object is like a message in a bottle, sent across the galaxy. 3I/Atlas carries information about processes, materials, and environments far beyond the solar system. Understanding its origin helps us understand not just this one object, but the mechanisms that shape planetary systems everywhere. Theories about its origin are thus more than academic speculation. They are windows into the dynamics of the galaxy itself, probing questions of planetary formation, stellar evolution, and interstellar transport. While no single theory can yet definitively explain the object's origin, the convergence of observational data, computational modeling, and historical comparison narrows the possibilities. Evidence supports a scenario in which 3I/Atlas was ejected from a distant star system under unusual conditions, potentially modified during an interstellar journey spanning millions of years. Whether as a fragment of a planetary collision, a body ejected from a binary system, or a survivor of rare cosmic phenomena, The object represents a rare and invaluable opportunity to study interstellar matter directly. Ultimately, the study of 3I/Atlas's origin exemplifies the interplay between empirical observation and imaginative reasoning in astronomy. While rigorous models constrain plausible scenarios, the object's anomalies preserve an element of mystery, compelling researchers to remain open to unexpected explanations. As ongoing observations refine understanding of its trajectory, composition, and behavior, the theories about its origin will evolve, reflecting both the object's uniqueness and the evolving knowledge of interstellar dynamics. 3I/Atlas is more than an object. It is a messenger, a challenge, and a catalyst for expanding the horizons of modern astronomy, inviting scientists and enthusiasts alike to consider the vastness and complexity of the galaxy beyond our solar system. As 3I/Atlas moves deeper into the solar system, the question of potential threats inevitably arises, though astronomers are careful to emphasize that realistic risks are exceedingly low. Nevertheless, the combination of high velocity, unusual trajectory, and unpredictable behavior compels detailed analysis of possible interactions with planets, moons, asteroids, and even Earth itself. Understanding these potential impacts requires consideration of both statistical probabilities and the physical characteristics of the object, including size, composition, and trajectory deviations induced by gravitational interactions or outgassing. The first step in assessing potential threats is modeling the object's path with precision. Orbital simulations incorporate gravitational influences from the Sun and major planets, accounting for perturbations that could slightly alter 3I/Atlas's hyperbolic trajectory. While its high velocity ensures that it will pass through the solar system on a one-time transit, minor deflections from planetary encounters, particularly with massive bodies such as Jupiter or Saturn, could slightly modify the predicted path. Although a direct collision with Earth is extremely improbable, even small changes in trajectory could bring it closer to other solar system bodies, making careful monitoring essential. Astronomers frequently update these models as new observational data becomes available, refining both position estimates and velocity vectors. Statistical analysis provides further context. Based on current measurements, the probability of 3I/Atlas colliding with any major planet is vanishingly small. The vast distances between planets and the object's narrow approach corridor ensure that direct impacts are unlikely. Nonetheless, smaller bodies in the asteroid belt or the outer reaches of the solar system could experience gravitational perturbations if they pass near its path. Such interactions, while unlikely to produce catastrophic effects, could create minor deviations in orbital trajectories, potentially increasing the risk of future collisions among smaller objects. These considerations underscore why astronomers remain vigilant. Even when immediate danger is minimal, subtle effects in the complex gravitational network of the solar system warrant careful attention. Historical analogues provide valuable perspective. Objects such as Shoemaker-Levy 9, which collided with Jupiter in 1994, or smaller near-Earth asteroids like 2012 DA14, illustrate how celestial bodies can interact with planets, occasionally producing dramatic effects. However, 3I/Atlas differs significantly from these cases. Its hyperbolic velocity far exceeds that of bound objects, meaning that any gravitational interactions will be brief and limited. Unlike Shoemaker-Levy 9, which fragmented under tidal forces in Jupiter's gravitational field, 3I/Atlas is unlikely to be captured or disrupted by planetary gravity, and unlike near-Earth asteroids, it will not remain in orbit around the Sun. These distinctions are crucial in evaluating both the likelihood and the potential consequences of encounters. The object's composition also informs threat assessment. Observations suggest that 3I/Atlas is relatively small, likely only a few hundred meters across, and composed of a combination of rock, metal, and possibly volatile ices. Even in the unlikely event of an Earth impact, its size is insufficient to cause global devastation. Nonetheless, localized damage from an impact of this magnitude could be significant, analogous to historical asteroid impacts in Earth's geological record that produced regional devastation without global extinction. Scientists consider these factors carefully, modeling potential impact scenarios to assess energy release, trajectory effects, and possible atmospheric consequences. Gravitational deflection by planets is a central focus in threat analysis. Massive bodies like Jupiter and Saturn can exert measurable influence on fast-moving interstellar objects. Simulations demonstrate that a near pass by Jupiter, for instance, could slightly alter 3I/Atlas's trajectory, potentially increasing the likelihood of interactions with other small solar system bodies. However, the high velocity and steep angle of approach reduce the magnitude of such deflections, and simulations consistently indicate that direct collisions with planets remain unlikely. Even so, the possibility of minor perturbations emphasizes the need for ongoing observation and adjustment of predictive models, reflecting the dynamic and interconnected nature of celestial mechanics. The potential for collisions with moons or smaller satellites is also considered. Moons orbiting gas giants or other planets present relatively small targets, but in principle, a close approach could lead to surface impacts or generate debris. Such scenarios are of particular interest to astronomers studying planetary rings or asteroid capture phenomena, as even minor collisions can produce detectable effects. While the likelihood of these events is low, the study of 3I/Atlas provides an opportunity to refine models of small body interactions in the solar system, improving predictive capabilities for future interstellar or native objects. Atmospheric entry scenarios, though unlikely, are modeled to understand potential consequences. Should an interstellar object like 3I/Atlas enter Earth's atmosphere, its high velocity would generate intense heat and pressure, producing airbursts or localized ground impacts depending on size and composition. Historical events, such as the Tunguska explosion of 1908, demonstrate the potential for regional destruction even from relatively small celestial objects. However, current trajectory estimates for 3I/Atlas indicate that such an event is extraordinarily improbable. Nevertheless, preparedness for high-velocity impactors is an active area of research, and interstellar visitors like this one provide valuable data to test theoretical models under extreme conditions. Non-collision impacts also merit consideration. Close passes near planets or moons could produce gravitational perturbations, potentially altering orbital dynamics of surrounding smaller bodies or ring systems. While unlikely to have immediate consequences for Earth, these interactions are scientifically significant, providing insights into the behavior of small bodies in complex gravitational fields. Observations of such perturbations allow astronomers to test models of celestial mechanics and refine understanding of how fast-moving objects interact with planetary systems. Astronomers also emphasize the distinction between sensationalism and evidence-based risk assessment. Media reports often exaggerate potential threats, framing interstellar objects as imminent dangers, but the scientific community approaches 3I/Atlas with rigor and caution. While the object's unusual features and high speed make it an intriguing subject, probabilities of direct impact with Earth or major planets remain extremely low. Instead, the focus is on monitoring, modeling, and understanding potential secondary effects, both for scientific knowledge and for preparedness in the unlikely event of a closer encounter. In addition to direct physical threats, astronomers consider indirect consequences, such as potential collisions with human-made satellites or orbital debris. While the vastness of space makes such encounters highly unlikely, increasing satellite density in Earth's orbit makes high-velocity interstellar visitors relevant for long-term monitoring and modeling. Even minor interactions could offer practical lessons in orbital management, deflection probabilities, and impact mitigation strategies for future fast-moving objects. Finally, the study of 3I/Atlas's potential threats has broader implications for planetary defense. Interstellar objects, though rare, represent extreme cases for impact modeling due to their high velocities and non-circular trajectories. Preparing for such possibilities requires refinement of observational networks, rapid response capabilities, and robust simulation tools. Insights gained from monitoring 3I/Atlas, even absent any immediate threat, contribute to long-term strategies for understanding and mitigating risks posed by both native and interstellar objects. In conclusion, while the realistic dangers posed by 3I/Atlas are extraordinarily low, the object's passage through the solar system warrants careful analysis. Its high velocity, hyperbolic trajectory, and potential for gravitational interactions with planets, moons, or smaller bodies necessitate ongoing observation and simulation. Historical analogs and physical modeling inform assessments of collision risk, energy release, and secondary effects, while expert consensus emphasizes evidence-based evaluation over sensationalism. By examining potential threats rigorously, astronomers gain not only peace of mind but also critical insights into celestial mechanics, planetary defense, and the behavior of interstellar visitors. 3I/Atlas thus serves as both a scientific enigma and a practical test case, illuminating the interplay of probability, physics, and preparedness in a vast and dynamic solar system. The passage of 3I/Atlas through the solar system prompted an immediate and coordinated response from the global scientific community. Astronomers, planetary scientists, and space agencies recognized that the object's high velocity and unusual trajectory required continuous, high-precision monitoring to refine predictions, gather data, and anticipate any potential interactions with solar system bodies. Unlike typical near-Earth objects, which can be tracked over extended periods, interstellar visitors demand rapid, intensive observational campaigns due to their fleeting visibility and the speed at which they traverse the inner solar system. This urgency necessitated a level of international collaboration that is exceptional even by modern astronomical standards. Observatories across both hemispheres quickly synchronized efforts to maximize coverage. Northern and southern hemisphere telescopes worked in tandem, allowing for near-continuous observation despite the rotation of the Earth. Large optical telescopes such as the Very Large Telescope, VLT, in Chile and Keck Observatory in Hawaii conducted high-resolution imaging, capturing subtle changes in brightness and rotational dynamics. Meanwhile, survey telescopes like Pan-STARRS and Atlas continued wide-field monitoring, providing critical astrometric data to refine orbital parameters. This combination of targeted and wide-field observation allowed researchers to balance detailed analysis with comprehensive tracking, ensuring that no aspect of the object's movement went unnoticed. Space agencies also played a crucial role. NASA, ESA, and JAXA coordinated observational campaigns and shared real-time data across international networks. Satellites equipped with infrared sensors, such as NASA's NEOWISE and ESA's Herschel Space Observatory, where applicable, provided thermal data to help determine the object's size, albedo, and potential outgassing activity. Such measurements are invaluable for modeling trajectory deviations that could result from non-gravitational forces. Meanwhile, radio telescopes, including the Green Bank Observatory and the Parkes Radio Telescope, scanned for potential emissions or anomalies, offering additional insight into surface composition and activity. The integration of multiple wavelengths, optical, infrared, and radio, allowed a multidimensional view of 3I/Atlas, capturing nuances that single instrument studies might miss. Technological innovations were crucial in facilitating this rapid response observation. Advanced astrometric software enabled near real-time calculations of trajectory updates, integrating input from dozens of telescopes worldwide. Automated data pipelines processed imaging and spectroscopic observations to detect subtle changes in brightness, rotation, and reflectivity, while machine learning algorithms assisted in identifying anomalies and potential outgassing events. These tools reduced the lag between data acquisition and analysis, allowing astronomers to adjust observation schedules, refine models, and prioritize follow-up studies with unprecedented efficiency. The technological infrastructure supporting this effort underscores how modern astronomy depends not only on hardware, but also on sophisticated computational resources and global communication networks. Coordination extended beyond professional observatories. Amateur astronomers with high-quality equipment contributed valuable observations, particularly from locations that filled gaps in professional coverage. Networks such as the International Astronomical Union's Minor Planet Center facilitated the submission, verification, and integration of these observations into global datasets. This collaborative framework allowed scientists to maintain near-continuous tracking of 3I/Atlas, compensating for observational blind spots caused by weather, daylight, or geographic limitations. The collective effort demonstrates the value of distributed, community-supported science in monitoring fast-moving, transient objects. Scientific strategy also involved prioritizing observation windows based on trajectory predictions. Because 3I/Atlas was moving rapidly along a hyperbolic path, optimal observation times were brief, requiring precise coordination. Observatories targeted the object when it was both visible and at the best angle for high-resolution imaging or spectroscopy, balancing competing demands from other celestial programs. Astronomers also scheduled multiple, overlapping observations to reduce the risk of gaps in coverage, enabling continuous monitoring of brightness variations, rotational dynamics, and potential outgassing events. Such meticulous planning highlights the stakes involved. Missing even a brief window could result in lost opportunities to understand the object's behavior and characteristics. Communication among international teams was critical. Daily coordination calls, shared online databases, and real-time data visualization tools allowed researchers to compare findings, discuss anomalies, and adjust strategies collaboratively. This transparency minimized duplication of effort, ensured that emerging patterns were quickly identified, and facilitated rapid response to unexpected phenomena, such as sudden brightness spikes or potential radio emissions. In essence, the global scientific response functioned as a tightly integrated network, combining localized observation capabilities with centralized coordination and computational modeling to maximize scientific return. Beyond immediate observation, international teams engaged in long-term modeling to anticipate potential impacts on solar system dynamics. Computational astrophysicists used high-performance supercomputers to simulate millions of possible trajectories, incorporating uncertainties in velocity, position, and surface interactions. These simulations not only refined predictions of 3I/Atlas's path, but also allowed researchers to model secondary effects, such as minor gravitational perturbations on asteroids or interactions with planetary ring systems. The outputs of these models informed observation strategies, guiding where and when telescopes should focus to capture the most critical data. In addition to trajectory and photometric monitoring, spectroscopic studies became a central focus of the international effort. Teams sought to determine the object's surface composition, temperature distribution, and chemical signatures, which could reveal its origin and formation history. Observatories used high-dispersion spectrographs to detect subtle absorption or emission features, while infrared instruments mapped thermal profiles. Coordinating these studies across multiple wavelengths and instruments allowed scientists to construct a comprehensive, multidimensional understanding of the object's physical properties. This approach exemplifies the integrative methodology now essential in tracking and analyzing fast-moving interstellar objects. International scientific response also included contingency planning. While the probability of a collision with Earth is minimal, agencies used 3I/Atlas as a case study to test rapid coordination and predictive modeling in response to high-velocity interstellar visitors. These exercises enhance preparedness for future events, ensuring that observation networks, communication channels, and computational resources are ready to respond efficiently to transient celestial phenomena. In this way, the monitoring of 3I/Atlas contributes both to immediate scientific understanding and to broader planetary defense preparedness, illustrating the dual purpose of such collaborative efforts. The global response further emphasizes the interconnected nature of modern astronomy. No single observatory or space agency possesses sufficient coverage, instrumentation, or computational power to study an object like 3I/Atlas independently. By pooling resources, expertise, and data, international teams create a synergistic system capable of addressing the challenges posed by interstellar objects. This collaboration highlights the value of open data sharing, rapid communication, and coordinated strategy in advancing scientific knowledge under time-sensitive conditions. In summary, the international scientific response to 3I/Atlas demonstrates the effectiveness of coordinated observation networks, advanced technological tools, and real-time communication in studying fast-moving interstellar visitors. Observatories, space agencies, and amateur astronomers collaborate seamlessly to track, model, and analyze the object's trajectory, brightness, composition, and potential interactions. Sophisticated software, machine learning, and supercomputing resources enable rapid processing and predictive modeling, while overlapping observation schedules maximize coverage and minimize data gaps. This global effort not only advances understanding of 3I/Atlas itself, but also strengthens frameworks for monitoring future interstellar objects, illustrating the high stakes, precision, and collaborative spirit required to study these rare and enigmatic celestial phenomena. The announcement of 3I/Atlas and the unusual phenomena associated with it quickly captured the public imagination, sparking widespread discussion across social media platforms, news outlets, and online forums. The object's interstellar origin, high velocity, and enigmatic signals provided fertile ground for speculation, with theories ranging from plausible scientific interpretations to sensationalist and conspiratorial narratives. As the scientific community worked to observe and model the object, the public reaction unfolded in parallel, often blending curiosity, excitement, and fear. Social media played a central role in the dissemination of information and speculation. Platforms such as Twitter, Reddit, and TikTok became hubs where amateur astronomers, science enthusiasts, and casual observers shared updates, images, and video simulations. Viral posts highlighted 3I/Atlas's unusual trajectory, light fluctuations, and potential signals, often framing the object as a mysterious or potentially threatening visitor from another star system. While many users approached the topic with enthusiasm and scientific interest, the speed and virality of social media made it difficult to distinguish verified data from rumors or exaggerations. Memes, animated simulations, and speculative infographics contributed to the narrative, sometimes amplifying minor anomalies into perceived threats or signs of intelligent design. Mainstream media coverage further shaped public perception. Headlines ranged from measured scientific reporting to sensationalized claims designed to attract clicks. Some outlets focused on factual aspects, accurately conveying the object's interstellar origin, the rarity of such visitors, and the ongoing global observational efforts. Others emphasized the object's mystery or suggested potential danger, framing the story with dramatic language that could provoke fear or misunderstanding. In some cases, news stories presented conflicting interpretations, juxtaposing expert caution with sensational speculation, which often blurred the distinction between scientific fact and conjecture for casual readers. Misinformation quickly emerged alongside legitimate reporting. Unverified claims about 3I/Atlas's trajectory, size, or potential artificial origin circulated widely, sometimes drawing on previous interstellar objects such as Oumuamua as precedent. These narratives often included dramatic interpretations that were inconsistent with current observational data, suggesting scenarios like imminent collision with Earth or extraterrestrial technology. While the scientific community consistently refuted such claims, the rapid spread of misinformation demonstrates the challenges of public communication when extraordinary astronomical events intersect with social media amplification. The contrast between sensationalism and careful reporting highlights the importance of scientific literacy. Experts consistently emphasized that while 3I/Atlas presents unique observational opportunities, the likelihood of direct impact or immediate danger is extremely low. Statements from NASA, ESA, and leading astronomers stressed the object's scientific significance and rarity rather than promoting fear. Educational outreach, including press releases, public lectures, and online Q&A sessions, helped clarify uncertainties and provide context for observational data. These efforts mitigated some of the public's anxiety while reinforcing the collaborative and methodical nature of astronomical research. Public fascination also centered on the potential for 3I/Atlas to provide insights into alien planetary systems. Speculation about its chemical composition, surface features, and unusual signals fueled imaginative narratives about what the object might reveal regarding the broader galaxy. Science communicators used this interest to explain complex concepts, such as hyperbolic trajectories, gravitational perturbations, and interstellar chemistry, translating cutting-edge research into accessible narratives. While social media and sensational headlines often emphasized mystery and uncertainty, structured science communication provided a more balanced understanding, highlighting both the excitement and the caution required in studying such rare interstellar visitors. Pop culture influence further shaped perception. References to science fiction, alien encounters, and interstellar travel appeared in commentary, memes, and videos, connecting the scientific event to familiar narrative frameworks. This phenomenon illustrates how cultural context influences interpretation. Extraordinary astronomical events often become intertwined with pre-existing notions of space exploration, extraterrestrial intelligence, and cosmic risk. While this can enhance public engagement, it also contributes to conflated narratives in which imagination sometimes overshadows data-driven analysis. Interestingly, the pace of public engagement created feedback loops influencing media coverage. Viral social media posts, often exaggerating minor anomalies, prompted journalists to follow trends, leading to repeated coverage of the most sensationalized elements. This dynamic occasionally forced scientists to respond publicly to clarify misconceptions, issuing statements, interviews, and explanatory articles. These interactions highlight the iterative relationship between science, media, and public perception. Each informs and reacts to the other, shaping collective understanding in real time. Amateur astronomers also played a role in bridging the gap between public curiosity and scientific observation. Observers equipped with high-quality telescopes contributed images and photometric data, some of which were shared online and occasionally incorporated into professional analysis. These contributions fostered a sense of inclusivity and participation in real science, allowing the public to engage actively with observations rather than remaining passive consumers of media narratives. This integration of citizen science helped counter some misinformation by emphasizing verifiable, reproducible data. Despite widespread fascination, experts cautioned against drawing premature conclusions. The unusual light curves, potential signals, and anomalous surface features are intriguing, but they require rigorous analysis before confirming any extraordinary interpretations. Statements from leading astronomers repeatedly stressed that interstellar objects are rare, their behavior can be unpredictable, and observed anomalies often have natural explanations. These repeated reminders underscored the need for patience, careful modeling, and multi-instrument observations before forming conclusions, balancing public curiosity with scientific rigor. Overall, the public and media response to 3I/Atlas illustrates both the opportunities and challenges of communicating extraordinary astronomical events. Viral speculation and social media amplification demonstrate the power of public engagement, while also highlighting the risks of misinformation and sensationalism. Scientific institutions responded with transparency, educational outreach, and ongoing updates, providing factual context alongside data to guide interpretation. Meanwhile, citizen science initiatives offered a way for the public to engage constructively, participating in observation and contributing to a collective understanding of the object. In conclusion, the interplay between media hype, social media speculation, and careful scientific reporting has shaped the public narrative surrounding 3I/Atlas. While sensational headlines often emphasized mystery, threat, or alien speculation, structured communication from scientists and space agencies provided accurate context, refined understanding, and reassurances regarding risk. This dynamic demonstrates the importance of clear, accessible science communication in the age of rapid information sharing. The public fascination, when channeled constructively, enhances scientific engagement, spreads awareness of observational astronomy, and underscores the global significance of rare interstellar visitors. By balancing curiosity, skepticism, and evidence-based reporting, the discourse surrounding 3I/Atlas reflects both the excitement and responsibility inherent in interpreting and disseminating information about extraordinary cosmic phenomena. The study of 3I/Atlas gains much of its urgency and intrigue when viewed in the context of previous interstellar visitors, particularly 1I/Oumuamua, discovered in 2017, and 2I/Borisov, detected in 2019. These two objects, the first confirmed interstellar bodies to pass through our solar system, provided unprecedented opportunities for astronomers to refine observational strategies, develop theoretical frameworks, and anticipate the challenges associated with tracking fast-moving, transient visitors from beyond the Sun's gravitational influence. Each offered unique insights, shaping the scientific response to 3I/Atlas and highlighting both the potential and limitations of current detection and monitoring capabilities. Oumuamua, a small, elongated object exhibiting a hyperbolic trajectory, startled the astronomical community with its unusual characteristics. Initial observations revealed a lack of a visible cometary tail despite its close approach to the Sun, contradicting expectations for a volatile-rich body. Its rapid rotation and extreme elongation challenged conventional understanding of small-body physics, while subtle non-gravitational acceleration hinted at previously unobserved mechanisms. The object's fleeting visibility required near-immediate mobilization of telescopes worldwide, emphasizing the importance of rapid response, international coordination, and real-time data sharing. The experience of tracking Oumuamua taught astronomers valuable lessons about the necessity of global collaboration and the critical role of flexible observation schedules for interstellar objects that appear and disappear quickly. Following Oumuamua, 2I/Borisov presented a contrasting case. Unlike its predecessor, Borisov displayed a visible, active cometary coma, confirming it as a more conventional volatile-rich interstellar visitor. This distinction allowed scientists to apply traditional cometary observation techniques, measuring gas emissions, dust production rates, and chemical composition. Spectroscopic studies revealed familiar elements such as cyanide, water, and various organic compounds, providing direct evidence of similarities and differences between solar system comets and those formed in other stellar environments. The comparison highlighted the diversity among interstellar objects and underscored that these bodies could vary dramatically in composition, structure, and behavior, further reinforcing the need for adaptable observational strategies. Lessons from these past visitors directly inform the response to 3I/Atlas. Both Oumuamua and Borisov demonstrated that interstellar objects can be detected only briefly and often with little warning, making continuous sky surveys and automated detection pipelines indispensable. Wide-field survey telescopes such as Pan-STARRS, Atlas, and other ground-based instruments played a decisive role in identifying these objects, while follow-up observations with larger, high-resolution telescopes allowed detailed analysis. For 3I/Atlas, astronomers applied these same strategies but expanded them, incorporating lessons learned regarding rapid multi-wavelength observation, continuous astrometric tracking, and real-time international collaboration to ensure that every moment of visibility was maximally leveraged. Both previous visitors also highlighted the importance of modeling potential non-gravitational forces. Oumuamua's subtle acceleration suggested mechanisms beyond simple gravitational dynamics, such as outgassing, radiation pressure, or even structural irregularities affecting its trajectory. Borisov's more conventional cometary activity confirmed the significance of outgassing as a trajectory-altering factor. These examples informed the modeling of 3I/Atlas's path, encouraging astronomers to account for potential non-gravitational effects, surface variability, and rotational dynamics that could influence predictions of its trajectory through the solar system. By applying insights from these cases, predictive simulations for 3I/Atlas became more sophisticated, integrating factors that would have been overlooked if prior experiences were ignored. Another key lesson is the role of chemical and spectral analysis in determining origin and formation history. Spectroscopic studies of Borisov allowed astronomers to compare elemental abundances with those of solar system comets, revealing both similarities and differences that inform models of planetary system formation beyond the Sun. While Oumuamua presented fewer spectroscopic opportunities due to its faintness and rapid motion, the combination of observational and modeling data still provided constraints on composition and albedo. For 3I/Atlas, these precedents underscore the value of multi-instrument, multi-wavelength analysis, enabling scientists to detect subtle variations in surface reflectivity, chemical composition, and possible outgassing events that may provide clues about its stellar origin. Public and media response to Oumuamua and Borisov also shaped the scientific approach to 3I/Atlas. The intense attention given to both objects demonstrated that rapid communication of discoveries is essential to manage both public curiosity and misinformation. Scientists recognize the importance of clear, factual reporting alongside media engagement, ensuring that observational data, probabilistic assessments, and potential risks were communicated accurately. The combination of rigorous scientific work and public education efforts contributed to a more informed discourse, reducing speculation while fostering engagement, a strategy fully applied to the monitoring and reporting of 3I/Atlas. Technological advancements between the detection of previous visitors and 3I/Atlas enhanced the response capabilities. Automated detection algorithms, machine learning tools, and high-speed data processing now allow for faster identification and characterization of moving objects, reducing the time between discovery and follow-up. Observatories can now coordinate in near real time, sharing astrometric data, photometric measurements, and spectral analysis globally, facilitating continuous monitoring across multiple continents. These advancements ensure that even a transient, high-velocity interstellar object like 3I/Atlas can be tracked with unprecedented precision, minimizing observational gaps that would have been unavoidable just a few years ago. Lessons from prior interstellar encounters also informed modeling of potential interactions with solar system bodies. The hyperbolic trajectories of both Oumuamua and Borisov required careful computation of gravitational perturbations and potential collisions with planets, moons, and minor bodies. While neither object posed significant risk, simulations developed during these studies established a framework for evaluating potential threats posed by future visitors. For 3I/Atlas, astronomers applied these modeling techniques to assess close approaches, possible perturbations, and the impact of non-gravitational forces, enabling evidence-based evaluation without resorting to sensationalist predictions. Additionally, prior interstellar visitors illustrated the diversity of possible object types, emphasizing the need for flexible theoretical frameworks. Oumuamua's elongated, seemingly inert nature contrasted sharply with Borisov's active cometary behavior, demonstrating that interstellar objects may encompass a broad spectrum of physical and chemical characteristics. This diversity reinforced the principle that no single template can describe all interstellar visitors and that observational strategies must adapt quickly to novel features. With 3I/Atlas, scientists applied these lessons, preparing for unexpected properties such as irregular rotation, unusual reflectivity, or anomalous signals, while ensuring observational flexibility to capture every available detail. Ultimately, the study of past interstellar visitors established the urgency and scientific priority for objects like 3I/Atlas. Each previous encounter provided incremental improvements in detection methods, trajectory modeling, chemical analysis, and international coordination. The combined experience of observing Oumuamua and Borisov created a blueprint for rapid response campaigns, comprehensive multi-wavelength monitoring, and careful public communication, lessons that were fully operationalized in the global effort to track 3I/Atlas. In conclusion, the legacy of Oumuamua and Borisov frames our understanding of 3I/Atlas as both a scientific opportunity and a logistical challenge. These prior objects taught astronomers about the fleeting nature of interstellar visitors, the importance of rapid and coordinated observation, and the need for adaptable models accounting for unusual behavior and non-gravitational forces. They also highlighted the importance of public communication and careful differentiation between sensationalism and rigorous analysis. By building on these lessons, the astronomical community has approached 3I/Atlas with a level of preparedness, technological sophistication, and international cooperation previously unattainable, maximizing the potential to extract meaningful scientific knowledge from this rare and enigmatic interstellar traveler. The observation of 3I/Atlas is far from complete. As it continues its rapid transit through the solar system, astronomers are carefully planning both immediate and long-term strategies to maximize scientific return. Unlike previous interstellar visitors, whose brief visibility left significant gaps in data, 3I/Atlas benefits from heightened global awareness, advanced detection technologies, and an already established network of observatories coordinated for continuous monitoring. The future of its observation involves a combination of traditional telescopic imaging, spectroscopy, space-based instrumentation, and high-fidelity simulations, all aimed at unraveling the mysteries of its origin, composition, and trajectory. One of the primary goals for ongoing observation is to refine the object's trajectory with exceptional precision. While initial orbital calculations provide a general path through the solar system, astronomers continue to update models using real-time astrometric data. Each new observation, whether from large ground-based telescopes or space-based instruments, reduces uncertainty in position and velocity vectors. The high speed and hyperbolic path of 3I/Atlas mean that even minor adjustments in trajectory can have significant implications for predicting future positions, potential close encounters with minor solar system bodies, and understanding the object's past journey through interstellar space. By continuously refining these calculations, scientists aim to construct the most accurate three-dimensional representation of its motion, enabling precise simulations of both past and future dynamics. Spectroscopic analysis remains a critical component of future research. Understanding the composition of 3I/Atlas can provide clues about the environment in which it formed and the processes it has undergone during interstellar travel. High-dispersion spectrographs on telescopes such as the Keck Observatory, the Very Large Telescope, VLT, and space-based platforms can detect subtle absorption and emission lines, revealing elements and compounds present on the surface or released through potential outgassing. In particular, astronomers are interested in detecting volatile compounds, organics, and unusual minerals that could indicate formation around a star system different from our own. Such data would not only illuminate the history of 3I/Atlas but also enhance understanding of planetary formation processes in other stellar systems. The integration of multi-wavelength observations is another focal point of ongoing research. Observing 3I/Atlas across optical, infrared, and radio wavelengths allows astronomers to capture different aspects of its physical and chemical properties. Optical imaging provides information on rotation, shape, and surface reflectivity, while infrared data can detect thermal emission and quantify size and albedo. Radio observations may reveal anomalous emissions or interactions with the solar wind, offering insights into potential surface activity or material ejection. The combination of these observational modalities provides a comprehensive picture that no single wavelength could achieve independently, emphasizing the importance of coordinated, multi-instrument campaigns. Advanced simulations play a complementary role to direct observation. High-performance computational models are being used to simulate 3I/Atlas's passage through the solar system, incorporating gravitational influences from all major planets, minor bodies, and the Sun itself. These simulations also consider non-gravitational forces, such as outgassing or radiation pressure, which could subtly alter the trajectory. By exploring millions of potential trajectories, researchers can estimate uncertainties, assess probabilities of close encounters, and identify optimal observation windows. Simulations are also used to model surface properties, rotational dynamics, and potential fragmentation, providing predictive insight into phenomena that might be observed in real time. Looking further ahead, the possibility of dedicated space missions to study interstellar objects is under consideration. While 3I/Atlas itself may pass too quickly for a spacecraft intercept, proposals for rapid response missions are being evaluated to rendezvous with future interstellar visitors. Concepts include small, high-velocity probes capable of rapid deployment, flyby missions using gravitational assists, and instrumentation optimized for high-speed encounters. Even if 3I/Atlas cannot be directly sampled, these mission concepts highlight the long-term strategic planning of the scientific community, informed by the experiences of observing Oumuamua, Borisov, and now 3I/Atlas. The development of such missions could transform our understanding of interstellar material and provide in situ measurements unattainable through remote observation. Technological limitations, however, impose practical constraints. The faintness, small size, and rapid motion of 3I/Atlas challenge even the most advanced telescopes. Exposure times must be carefully balanced to avoid motion blur while capturing sufficient light for analysis, and spectroscopic resolution is constrained by signal-to-noise ratios at these distances. Furthermore, the availability of space-based instruments is limited, with competing demands from other missions and scientific priorities. To overcome these challenges, astronomers employ adaptive optics, image stacking, and data integration from multiple instruments to enhance signal quality and extract maximum information from each observation. Continuous software improvements, machine learning algorithms, and automated pipelines are also critical to process vast quantities of data quickly, ensuring that no opportunity for discovery is missed. Collaboration remains central to the future of 3I/Atlas research. Observatories across the globe coordinate schedules to provide near-continuous coverage, while space agencies share data and predictive models in real time. Citizen scientists and amateur astronomers contribute by monitoring brightness variations, capturing imaging data, and reporting anomalies, helping to fill geographic or temporal gaps in professional coverage. This integrated approach maximizes both temporal and spatial coverage, critical for an object moving rapidly along a hyperbolic path. The lessons learned from previous interstellar objects inform these collaborations, emphasizing flexibility, rapid response, and global communication. Uncertainties remain a defining feature of ongoing research. While models predict general behavior, subtle deviations in trajectory or unexpected surface activity could produce surprising results. Continuous observation is essential to detect such anomalies as early as possible, providing opportunities to refine models and adjust predictive simulations. Researchers remain particularly attentive to variations in brightness that might indicate rotational dynamics, surface heterogeneity, or outgassing events. Each new data point contributes to a deeper understanding of 3I/Atlas, incrementally reducing uncertainty and enhancing the predictive power of both observational and theoretical frameworks. One key objective is understanding the object's rotational state. Observations of light curves can reveal rotation periods, axial tilt, and potential tumbling behavior, which in turn affect non-gravitational acceleration and trajectory modeling. Accurate knowledge of rotation also informs compositional studies, as different regions of the surface may exhibit varying reflectivity or chemical signatures. Tracking these rotational dynamics requires high-cadence imaging and careful calibration, techniques honed through the study of past interstellar objects but now applied with even greater precision to 3I/Atlas. Ultimately, the scientific payoff from ongoing and future observation of 3I/Atlas extends beyond a single object. Detailed study of interstellar material informs models of planetary formation, stellar evolution, and the diversity of planetary systems throughout the galaxy. By comparing its properties with those of solar system bodies and previous interstellar visitors, astronomers can test hypotheses about chemical composition, surface processes, and the effects of long-term interstellar travel. Insights gained from 3I/Atlas may also inform broader questions, such as the prevalence of organic compounds in the galaxy and the mechanisms by which material is ejected from distant star systems into interstellar space. In conclusion, the future of 3I/Atlas observation represents a combination of urgency, precision, and ambition. Continuous astrometric tracking, multi-wavelength spectroscopy, computational modeling, and potential future missions together provide a comprehensive strategy for understanding this interstellar visitor. While technological and observational limitations impose challenges, international collaboration, rapid response strategies, and adaptive methodologies ensure that scientists are capturing the maximum possible data. The ultimate goal is to elucidate the object's composition, trajectory, and origin, providing insights into both its individual history and the broader nature of interstellar material. In doing so, 3I/Atlas will continue to enhance scientific knowledge, refine detection and observation techniques, and prepare the astronomical community for the next rare but scientifically invaluable visitor from beyond our solar system. The passage of 3I/Atlas through our solar system has captured the attention of astronomers, scientists, and the general public alike, not merely for its status as an interstellar visitor but for the many questions it raises about the nature of objects beyond our solar neighborhood. The reasons behind the sense of urgency and, at times, panic among astronomers stem from the object's combination of unusual characteristics: its hyperbolic trajectory, high velocity, mysterious signals, and potential interactions with solar system bodies. These factors collectively place 3I/Atlas in a category that demands immediate, sustained, and multifaceted scientific scrutiny. Unlike routine asteroids or comets, which can be observed over months or years with relatively predictable behavior, an object like 3I/Atlas offers only a narrow window for high-quality observation. This temporal limitation, combined with the uncertainty inherent in interstellar phenomena, underscores the heightened levels of alert and meticulous effort displayed by the global astronomical community. From its initial discovery, 3I/Atlas has defied easy classification. The very first observations revealed anomalies in brightness and trajectory that prompted researchers to refine traditional models of small-body dynamics. Its path, hyperbolic and distinctly non-elliptical, signifies an origin beyond the gravitational confines of our Sun, immediately distinguishing it from the countless objects that routinely orbit within the inner solar system. The apparent lack of similarity to previously catalogued bodies, along with unexpected rotational characteristics and potential outgassing events, amplified the scientific intrigue. This combination of rarity and uncertainty created an environment where every observation, every spectral measurement, and every data point carries enormous significance, informing both immediate scientific conclusions and long-term theoretical models of interstellar behavior. The global scientific response to 3I/Atlas exemplifies the collaborative and integrative nature of modern astronomy. Observatories from both hemispheres coordinated in near real time, ensuring continuous monitoring despite the constraints imposed by the Earth's rotation. Large optical telescopes provided high-resolution imaging, enabling precise measurements of rotational dynamics and light curves, while survey telescopes offered wide-field coverage to maintain accurate positional tracking. Space-based platforms, including infrared and radio observatories, contributed complementary data, providing insight into thermal emissions, potential outgassing, and surface composition. The integration of these resources represents a level of international cooperation and technological sophistication unprecedented in the observation of transient interstellar objects, demonstrating how modern astronomy has evolved to respond to high-stakes, time-sensitive phenomena. The multi-layered approach to observation also reflects the lessons learned from prior interstellar visitors. Oumuamua and Borisov illustrated both the challenges and opportunities presented by fast-moving interstellar objects. Each highlighted the necessity of rapid detection, adaptive observation strategies, and multi-wavelength analysis to capture fleeting phenomena. For 3I/Atlas, these lessons were operationalized on a global scale. Continuous astrometric tracking reduced positional uncertainty, high-cadence imaging revealed rotational patterns, and spectroscopy enabled tentative identification of surface composition and potential volatile activity. The combination of past experience and modern technology allowed astronomers to respond with unprecedented speed, ensuring that this rare object could be studied with a level of detail unimaginable just a few decades ago. Scientific fascination with 3I/Atlas is compounded by the mystery of its origin. Theories range from ejection from distant star systems due to gravitational perturbations, to remnants of collisions between massive bodies, to more exotic cosmic events not yet fully understood. Spectral analysis hints at chemical signatures that could illuminate processes occurring in other stellar environments, yet no definitive conclusion has been reached. This ambiguity fuels both scientific curiosity and the broader public imagination, as each new observation potentially reshapes understanding of planetary system formation, interstellar dynamics, and the prevalence of complex materials beyond the Sun's neighborhood. Equally important are the considerations of potential impact or influence on the solar system. While the probability of collision with Earth or major planets remains extremely low, astronomers must account for even minor gravitational perturbations affecting asteroids, moons, and other small bodies. Historical analogs, including prior interstellar comets, highlight the subtle yet measurable effects that fast-moving bodies can have on the orbital dynamics of smaller objects. These considerations, paired with precise trajectory modeling, explain the careful attention afforded to 3I/Atlas and the meticulous calibration of observational instruments. The stakes are not alarmist in a catastrophic sense, but are critically high in terms of data precision and predictive reliability, as each observation informs the broader scientific understanding of interstellar object behavior. Public perception and media coverage have added another dimension to the story. The unusual characteristics of 3I/Atlas, combined with social media virality and popular fascination with space and extraterrestrial phenomena, have resulted in widespread speculation. While some narratives veer into sensationalism or misinformation, these discussions also highlight the public's intrinsic interest in understanding the universe and our place within it. Scientists have engaged proactively, providing accessible explanations, clarifying uncertainties, and emphasizing the distinction between speculation and verified findings. This dialogue between experts and the public underscores the dual role of such discoveries. They are not only objects of scientific inquiry but also catalysts for broader cultural reflection and intellectual engagement. The lessons drawn from previous interstellar visitors continue to inform ongoing observation strategies. The need for rapid, coordinated monitoring, multi-wavelength analysis, and predictive modeling has been reaffirmed and refined in the case of 3I/Atlas. These measures not only optimize immediate scientific understanding but also prepare the astronomical community for future interstellar encounters. By systematically applying the knowledge gained from Oumuamua, Borisov, and now 3I/Atlas, astronomers create a continuous learning loop, improving methodologies, refining detection software, and strengthening global communication networks, all of which are critical for capturing fleeting interstellar phenomena. Technological limitations, however, remain a constant factor. Despite the extraordinary capabilities of modern telescopes and computational models, challenges persist in capturing precise measurements of faint, fast-moving objects. Exposure times must be optimized to avoid motion blur, spectral resolution is limited by signal strength, and space-based resources are constrained by operational schedules and competing scientific priorities. Nevertheless, adaptive optics, real-time data processing, and automated pipelines mitigate many of these constraints, enabling astronomers to extract maximum information from limited observation windows. This intersection of technology, methodology, and human ingenuity exemplifies how contemporary astronomy balances ambition with practical constraints. Looking beyond immediate observation, 3I/Atlas invites profound reflection on humanity's place in the cosmos. The very notion that objects from distant star systems traverse our solar neighborhood underscores the vastness and dynamism of our galaxy. It challenges assumptions about isolation and permanence, reminding us that our planetary system exists within a broader, interconnected interstellar environment. Each discovery of an interstellar visitor provokes both excitement and existential contemplation, as we confront evidence of materials, processes, and phenomena originating far beyond the sun's gravitational influence. In this sense, 3I/Atlas serves as a tangible reminder of the universe's scale, complexity, and ongoing evolution, inviting both scientific investigation and philosophical reflection. Moreover, the study of 3I/Atlas exemplifies the human capacity for curiosity, collaboration, and adaptation. Astronomers worldwide have mobilized resources, shared data, and applied cutting-edge technologies to capture every possible insight from a fleeting visitor. The resulting synthesis of observation, modeling, and interpretation demonstrates how collective expertise can transform a brief cosmic encounter into an enduring contribution to knowledge. It also illustrates the interplay between urgency and precision. Scientists must act quickly to exploit short observation windows while maintaining rigorous standards of measurement, analysis, and peer review. Finally, the story of 3I/Atlas resonates with both scientific and cultural dimensions. On one hand, it embodies the thrill of discovery, the challenge of uncertainty, and the intellectual satisfaction derived from solving complex celestial puzzles. On the other hand, it evokes a broader awareness of our place within an immense and active universe, prompting reflection on the fragility, curiosity, and resilience inherent to life on Earth. The combination of empirical investigation, technological innovation, and human imagination ensures that 3I/Atlas will occupy a significant place in both scientific history and public consciousness, serving as a focal point for inquiry, reflection, and wonder. In conclusion, astronomers are panicking not in a sense of fear, but in recognition of the extraordinary demands posed by 3I/Atlas. The urgency to observe, the challenge of understanding an unfamiliar object, and the necessity of global coordination to capture its fleeting journey. Its mystery, potential for interaction, and the insights it offers into interstellar processes make it a high-priority object of study. The international scientific response, informed by lessons from previous visitors, demonstrates the power of collaboration, rapid adaptation, and technological ingenuity. Simultaneously, public fascination and media discourse reflect humanity's enduring curiosity and the cultural significance of encountering the unknown. Above all, 3I/Atlas reminds us that we inhabit a dynamic universe, where the boundaries of knowledge are continually expanded by transient but invaluable visitors from the depths of interstellar space, inspiring both awe and intellectual vigilance as we strive to comprehend our cosmic context.